Okay, so welcome back. So we continue. So let me just remind you. Last time was a very long class. Sorry about that. I wanted to finish the. I wanted to finish the this last result. So let's just quickly recap. First of all, the determinant is a multiplicative. So determinant is a function. It exists and is unique for every field in every dimension. We completed the proof of existence last time by induction. Then you have we computed or whatever the determinant of A transpose. We proved that was equal to det A, either invertible or not, two cases. And then we said that A inverse also was, we computed that. And then we moved on to triangular matrices, except more generally, we looked at block triangular matrices. And we proved that the determinant is equal to this thing, where each Mij is of some fixed structured size, f to the ki plus kj. Okay, so that means each MII is a square matrix, and so you can take the determinant, and we did. Okay, so now let's continue. So beyond this, we looked at some corollaries as well. So the corollary is a block diagonal matrix, a block lower triangular matrix, and these corollaries. So I think there were probably three corollaries. So let me start with corollary 4 and 5, and then we get to Cramer's rule, and then we will start eigenvalues today. Okay, so corollary 4. Okay, so corollary 4 is the okay. So maybe I should remind you. We also know what the determinant was. The determinant is equal to that expansion along the column dg, right? So recall. We also saw, or in fact proved, by induction that the determinant of a matrix A, n cross n or whatever, is equal to summation I goes from 1 to n, negative 1 to the I plus j, Aij, determinant of a smaller dimensional matrix. Okay, where these were the matrices capital Aij, where you remove the ith row and the jth column of capital A. Okay, so this was called the column expansion. But now, because we know the transpose, we can talk of the row expansion, right? So corollary 4, the determinant of A is also equal to summation j goes from 1 to n, negative 1, it's the same thing, but j going from 1 to n, Aij, the determinant of Aij. And that is obvious because proof, using this, let me call this star. Basically, I take transposes twice. Okay, so let's call this. Remember, we had a name for this. This was called dj of A, right? So let's start with the left hand side and then just translate to the right hand side. First of all, I need to take A transpose. Now I take is equal to dj of A transpose. No, now you see this was dj. It was being summed over all I, but j was being held fixed. Here I is being held fixed, so let's call it di of A transpose. And instead of summing over I will sum over j. It doesn't matter what I sum over. So this is equal to summation j goes from 1 to n. I should have started by saying LHS equals. Left hand side is this thing, which is this. This is precisely exactly this expression with a minor change. So what am I saying here? Okay, I plus j, and then you see I'm summing over I, I'm fixing j, I want the ijth entry of the matrix. Here I'm summing over j and fixing I, so I want the jith entry of the matrix A transpose. First of all, the AJ entry and then determinant of the rest. Okay, so this is just the entry, but this entry is precisely Aij. And this A transpose Ji, this matrix here is precisely Aij. Take this matrix and take its transpose. But now the determinant of any transpose is equal to the determinant of the same matrix, and so you get the right answer. I mean, and probably like maybe I should simplify a step here, but it's obvious what that step is. This term is this. This is det of Aij transpose. And this is precisely because that I can remove the transpose because of the det, and that is precisely this expression. Okay. The next one I will just state, but I would have to say many more things to sort of make sense of it, so I will not do so. But let me just show you what I mean. So I will write it down explicitly for 3 by 3 matrices, and then work it out. Tell you the general formula. Let's look at the 3 by 3 matrix and calculate its determinant. This is the permutation, what I forget, it's called the Laplace representation of something of a determinant. So corollary 5, I guess. But before we get to corollary 5, let's look at the example of 3 by 3. Let's say you have A equals, I'll just call them A, B, C, D, E, F, G, H, I. Let's say I expand along the first row, just for fun. So then the determinant of A equals. Now I'm doing row expansion, so therefore I'm using corollary 4. I could also do the column expansion, it doesn't matter. So I'll just do row expansion. So A times, sometimes you write down square bracket, just vertical bars for determinants. Okay, so this is just A times. Now remove the first row in the first column, you get E of Hi times -1 to the 1 plus 1. Right? This is the 1 comma 1 entry. So -1 to the 1 plus 1 is 1. So this is E, F, H, I. Then you have -1 to the 1 plus 2, which is a negative B times the determinant. Remove these two. So D, F, H, I. Oops, something is very wrong. No, that D, F, G, I. And then again, -1 to the 1 plus 3 is -1 to the 4, which is plus 1. And then D, E, G, H. Okay. And now, of course, now I know the formula for a 2 by 2 determinant, so I can work this out. And what I get is precisely this is what happens when you get a new eraser. Works much better. Okay, so this is A, E, I minus A, F, H minus B, B, I plus B, F, G plus C, D, H minus C, G. There are these 6 terms that you get equals. And the point is, no matter which row or which column you expand along, you will get the exact same expression. That is obvious because the determinant is unique. So whatever you do, it's unique. Yeah, you get the same thing. But now you see, this is actually a sum over 6 terms. And let's look at the terms. Okay, so term number 1 is, I'll write these down. So A, E, I. Okay, the terms occur in different rows and different columns. A, F, H, D. Our DDI, BFG, CDH, and then CEG. You see that each of the 6 terms corresponds to the entries of the matrix that occur in different rows and columns. And there are exactly 6 possible such configurations where I can choose. So, if you have heard of rook, if you have seen chess, and you are asked how do you place rooks on a chessboard so that no 2 rooks can kill each other and every row and every column should have it. But no 2 rooks should kill each other. How many rooks can you place on an n cross n chessboard? Well, the answer is you have to place at the most 1 rook in every row. So there are at the most n of them you can place because the rooks can kill the hathi, rooks, whatever you call them, can kill each other on say, the same row. And also every rook, same row and also in every same column. So you have to place at the most n rooks on an n cross n chessboard. And in fact, you can place exactly n rooks if you make sure to avoid. So for example, all the rooks can be placed on the diagonal. or they can be placed for n equals 3 in exactly these 6 possible positions. In fact, the total number of positions, since you guys have taken the bridge course in semester 4, the undergrads at least, is n factorial. Right? For each row, you figure out some particular place where you can keep the rook, and then the first row has n options, the second row has n minus 1 options, because you can't repeat the first row's position. The third row has n minus 2 options, and all the way down to the last row having exactly 1 option. And so this is literally rook arrangements on a chessboard. There are n factorial of them. For n equals 3, you have 3 factorial, and these are exactly the 3 factorial positions. These are all the 3 factorial positions. Where rooks can be placed. I mean, I will not write more than that, such that no 2 rooks kill each other, etc. Okay, fine. So the point is, these are all the So this and these basically, there's a formal name for that outside of chess and inside mathematics. These are called permutations. Right? You are rearranging. So for the first row, you have 1. The first row is going to 1. The second row is going to 2. The third row is going to 3. In the third row, which column is occurring? In here, the first row, it occurs in the first column. The second row, it occurs in the third column. And the third row, it occurs in the second column. And you can write all these down. This one is precisely 3 to 1. There's something called the longest word in the while group. This is also a very different lecture, very different course. But yeah, so the point is, all these are all the 6 possible permutations. Or bijections of the set 1, 2, and 3. Okay? So these are all the positions where these things can be placed. And so basically, for every such permutation, you can actually write down a matrix. And the matrix is very, very simple. The matrix is precisely the ones where you place, you take the 0th power of these entries. Each corresponds to a permutation matrix. With zeros and ones. So for instance, I'll tell you what the matrices are. This is the identity matrix. The next one is, you get the idea. Okay. And each of these matrices has the nice property that the inverse equals its transpose. These are called orthogonal matrices. And this one is of course 1, 1. Each matrix, each of these matrices P satisfies P transpose, P inverse equals P transpose. So in particular, each matrix is invertible. And so what can the determinant of P be? It's a real number. Clearly, all these things are integers. So all the determinants are real numbers. And what can you say about the determinant? You can say that the determinant of P square, let's look at this. Look at the square of the determinant of P. On the one hand, this is equal to determinant of P times determinant of P. And the second P I will make as the transpose. And now what that is by multiplicativity, this is determinant of P times P transpose. And P times P transpose is the identity matrix. This is 1. So you have a real number whose square is 1, which means each determinant is plus or minus 1. Every permutation matrix and not just 3 by 3, but n from n by n. The depth of this. Okay, and now with this formula, I can tell you the expansion of the determinant. It's basically exactly like this one in the 3 by 3 case. So it's going to so in 3 by 3 case, so for A 3 by 3, the determinant of A is summation det of P, P a permutation matrix, and then, okay, so maybe I should not do this. Maybe I'll do it slightly better. Okay, so now to write down what this means, how to write down the formula, let's first, let me introduce one last piece of notation, the group, the set of permutations, which actually you can say is a group because you have composed two of them. But anyway, let Sn denote the set, in fact the group, if you have done algebra 1, of permutations or bijections of f functions going from 1 through n to itself. In fact, people usually say this, we term these as sigma or some Greek letter like that. Okay? And then for each permutation, of course, you have the permutation matrix. For each sigma, 1 goes to sigma of 1, 2 goes to sigma of 2, and so on. N goes to sigma of n. We have the permutation matrix. P sigma, which is just the ijth entry is 1 if j equals sigma of I and 0 otherwise. Right? So, I mean, if this is 1, 1, if this is 1, 2, 3 and 1, 3, 2, then you only take the 2, 3 and the 3, 2 entries. Otherwise, you take 0 and so on and so on. Okay, so you call that P sigma and then you can do the following. Then you have the following formula, and that is what I want to say. And that is exactly this formula that I wrote down here for 3 by 3. Then I have corollary. Five, I guess. Determinant of A n cross n is the summation over all the permutations. There are n factorial many of them. So you take all the possible things you can do. You take minus 1 to the, sorry, no, you take det of P sigma. Okay? And then you multiply this determinant by I goes from 1 to n, A, I, sigma I. Like Aij. So this is exactly the ACB, ACEG, that kind of thing. That is this part. And this is the plus or minus 1 depending on how the permutation looks like. This is the formula for a determinant. This is the explicit general formula for a determinant which is non-recursive. Or non-inductive. Okay. So that is that. Okay, so finally the last thing to do before we start with eigenvalues is Cramer's rule. And again we go back to solving linear systems of equations, which is how we started the course. Okay, so that's Cramer's rule. Let's see, let me start with these friends. Okay, so before we get to Cramer's rule, let me make some reference to Cramer's rule. I need to first define the adjugate matrix. I'm not sure if I defined it in the homework or not, but if not, you will get it in this week's homework. The adjugate matrix of a matrix A. So given A belongs to F to the n cross n, Its adjugate matrix, of course. Sometimes people just say adjugate is. So, sorry, adjugate matrix, sure, is ADJ of A. Some people think this is adjoint, but no, this is adjugate. And this, first of all, what is this? It's a matrix. It's also a matrix of the same size with I comma j entry. What I do is I look at the formula for the determinant and I take that remaining part. -1 to the I plus j. But then I take the remaining part with the transpose. So I take determinant, not aij, but aji. That is the important distinction note. Okay, so it's determinant of aji. Okay, now what do I want to say? Homework. This is not a thing, this is literally a homework problem. But it's a calculation again that everybody should do once in their life. So this is the course in which you have been selected to do the calculation. If A is invertible, again, meaning A is invertible, so A first of all belongs to, no, so of course F, first of all A is square. Then there is an explicit formula. This adjugate matrix is extremely similar, close to your inverse matrix. This is literally a scalar multiple of the inverse matrix, and that scalar is exactly the determinant or the reciprocal. Then A inverse is equal to determinant, because A is invertible. This is a non-zero element of the field. It has a reciprocal. Times the adjugate. This is the formula, explicit formula in terms of determinant. So, of this thing, which means what? So, in other words, if you look at the ijth entry of A inverse, I should write this down in my notes as well. Then what is it? Try to find out, right? So, this is -1 to the I plus j, that A ji by that A. And the divided by is just the sign of that it's a reciprocal. There are no fractions in the general field, but divided by just means multiply by the reciprocal, and that's what it is. That's a homework. It's literally, and how do you verify that something like this happens? You check that, A times B is the identity matrix. You should also check that B times A is the identity matrix, but that's fine. So just I'll ask you to check it one day at least, just like in the midterm I asked you to check something one day. Okay. Great, so now that is that. So now we get to Cramer's rule. So Cramer's rule. So suppose we want to solve Ax equals B. Again, A is n cross n, so yeah. And I know that A is invertible. Suppose I already know that my matrix A is invertible and I want to solve Ax equals B. So what do you do? Well, what you can do is, well, you know what the answer is. Maybe we'll just write this down. I know. Let us just write this down. So x equals, we know this, x equals A inverse B. But what does that mean? What is A inverse B? Right? So A inverse B is this, the determinant of A inverse. So by the homework problem, which I just stated, it is again the associativity of matrix multiplication and whatever the scalar comes out, it's this matrix times this vector. And so let's look at the coordinates. Look at the ith coordinate. Yeah. So for 1 less equals I less equals n, xi. Let's look at the ith coordinate of x. So it is of course that the scalar space. So determinant of A reciprocal times. Now what is the ith coordinate of this? You just write down the entries. So summation j goes from 1 to n. Adjugate of A jth, so ijth entry times jth entry. So there's a bj here. And then the adjugate ijth entry, I just wrote down somewhere here, this one. Minus 1 to the I plus j then AJI. This is by the definition of the adjugate matrix, by the obvious definition of matrix multiplication, and then the okay. And now what do I do? So let's maybe do an example of this. I'll leave this space open for the general formula, but let's do a 3 by 3 example again, just to show you how this looks like. I mean, again, you may remember this from your high school or middle school or whenever Cramer's rule you saw from the high school. But let's just do this again. Okay. Okay, I'm going to write this down in some way. It is going to be the determinant of some matrix divided by the determinant of the matrix A. And I think times of no times nothing. Times nothing. That's the whole point. Okay, let's take a look at this example. So example n equals 3. Okay, so what should we do? So n equals 3. So write this down. Fine. Okay, let me write down, let's say, and I equals 2. Why are these pens finishing? Fine. I equals 2, n equals 3. Let us write this down. So I want to interpret this as the determinant of a matrix. And it's very clear what it should be, right? So AJI is the thing with the jth row removed and the ith column removed. But I'm summing over the j. So I'm putting in all the j's. Yeah, I'm putting in all the jth row is being replaced. So yeah, let's look at this matrix 1 1 A1 2 A1 3. Am I doing this correctly? Something is very wrong. No, I thought the column was supposed to be replaced, but let me see. The I is fixed here. The I is always the second column, and it's the second column. The J's are running across each row. I think this is correct. Maybe I'm wrong. Let's I'll just verify it. Right? So basically, I write down the first column correctly, the third column correctly, and the second column I replace by the B's. And let's now expand this along the second column. So what do I get? Det of this, if you will, equals along the so it's minus 1 to the minus 1 to the 1 plus 1 plus 2 b1 times the det A21, A23, A31, A33, minus plus minus 1 2 plus 2, B2, A11, A13, A31, A33, and then plus whatever for B3. Okay, so let's just check. Is this consistent with this notation? So what is this? This is the matrix, which is A, of course, it's det of that. I mean. It's the matrix with what removed? The first row is clearly gone, and the second column is gone. First row, second column is gone. This one is the second row and the second column. And then this one will be the third row and second column. B3 is there. So third row and second column. So therefore what you will get is this is equal to, this whole thing is equal to summation. I'll just call it, let's call it k goes from 1 to 3 minus 1. Let's go on to call it, no, the summation that was j. So let's call it j and check the inverse. J goes from 1 to 3 minus 1 to 2 plus j. So I is 2. That is the hope. That is the hope. Now b j, that is correct. This 1 corresponds to 1. This 2 corresponds to 2 and the 3 to 3. So it's 2 plus j and bj. Okay, and now the determinant a, and now you see the 2, something is very wrong here. The third row and second column. My apologies. So the 2 stays the same and this is the j here. Right. Great. And so that's exactly what we had here. I equals 2 and you sum over j and you get exactly this formula. Okay, thank you. I was just going mad. What am I missing? Okay, so this is correct. So the idea basically is exactly that. You replace the ith column, although normally you think of I and rows and columns and so on. You replace the ith column by the vector b. So that's what you do here. So let's in fact better is this way. And this is det a I by det a comma where, and now I'll write this down. And that is the mistake I seem to have made here. Yes, that is the biggest mistake was that. I wrote down aj by a, and that's why I kept confusing. But actually, no matter what I write down in my math, at least I remember somewhat. So I can remember this, where ai equals matrix obtained by replacing the ith column of A normally we associate I with rows. If you want, you can talk of the ith row of A transpose. By replacing the ith column of A by B. This is Cramer's rule. That's literally Cramer's rule. So, corollary or the proposition, let's call it proposition. I'll just say that in general. I mean, you should see a statement of Cramer's rule. So, say A in F in cross N is invertible, then AX equals B if and only if. So B is a given vector in F to the N if and only if Xi equals det AI by det A for all I. That is Cramer's rule. Okay, now I think I'm actually done with one more thing, I think. One last thing before we get to eigenvalues. So yeah. Okay, Okay, good. So what to do? So the last thing is the following. It also involves the determinant, but now we have talked so far only about determinants of matrices. What about determinants of something which is less information than a matrix, but it really is a matrix in disguise, namely of a linear transformation. So what we have seen earlier is that if you take any matrix, then that denotes the process of pre-multiplying by such a matrix takes any n by 1 vector to an n by 1 vector. So it's a map from Fn to Fn. It's a linear transformation with a preferred choice of basis, ordered basis, namely the standard ordered basis. I can do the same thing with a different basis, or I can not involve the basis at all, and then I would get a linear transformation without any choice of basis, so it will not have a matrix representation. It is still a linear transformation from a finite dimensional vector space to itself. That corresponds to a square matrix. And of course, such a transformation can be invertible as well, or it cannot be, it need not be invertible, like the zero linear transformation. And then you can again ask, does the notion of a determinant make sense? So it turns out remarkably that it does, and for a sort of very simple reason. Let me tell you the notion of a determinant for a general finite dimensional vector space and a general linear transformation. So definition, let V be finite dimensional vector space over F over a field F. Good. Yeah. And T belongs to lim. Maybe this is not a definition, it's actually a proposition. Why should I define and then again separately say proposition? Okay, and T belongs to lim dB. Then, how do I want to state it? Okay, sorry. This thing, comma, I'll just put one the ingredient here itself. T belongs to lim dB, of course. And B is an ordered basis. Or let's say B and B prime are ordered bases. Bases or bases of B. These are, of course, finite sets. Then, you look at the matrix of T with respect to B, sorry, not the matrix, the determinant. So take the matrix of T with respect to B, comma B. Take the matrix of T with respect to B prime, comma B prime. Look at the determinants. And there you go. So in particular, therefore, you can define the determinant of T as to be either of these. It doesn't to be as follows: take any ordered basis, take the matrix with respect to that basis, take the determinant. I define that to be determinant of T. And by this proposition, it doesn't matter which ordered basis you take. You always get the same answer. That is the definition. So as a consequence, we have the determinant of T is defined to be the determinant of T with respect to any ordered basis. For any ordered basis. So of course, again, I'm not writing down all the same things again, but this V is a finite dimensional vector space and T is in V. Then with that notation, the determinant of T makes sense. Of course, it doesn't make sense if V is an infinite dimensional vector space. I'm not looking at determinant of T in that case. Okay. Proof. The proof is also very simple. The proof of the proposition, of course, not of the definition. The proof is let's write down the change of basis matrix from. I wrote it down one way, so let me write it down one way. Identity from B to B prime or B prime to B. Yes. Okay. So, and then we can write down the calculation, the cancelling calculation. Then I know what this is, right? So then I know that T B prime to B prime is what it is. First B prime, so it is P times the matrix T B prime B, sorry B B B times P inverse. And note that P is invertible, of course. We have already seen this. What is the inverse of P? It is the identity matrix, identity transformations matrix with respect to the bases B and B prime in the reverse order. So first of all, P is invertible, and we know that this is true. But now we simply calculate the determinants. Now it is, the determinant is multiplicative, and so this is equal to determinant of P times determinant of TDB times the determinant of B inverse. And we already have seen by some corollary of the main theorem on determinants that these two are reciprocals. So because they are reciprocals, they cancel, and so you're done. By the theorem on determinants plus its corollary. I think it was corollary 1. Okay, so that is the theorem. Okay, so now we can continue and finally move on to eigenvalues, for which I will change colors. And the point is, this particular result is going to be useful in talking about eigenvalues when I talk of eigenvalues of linear transformations, okay? Not of matrices, of course. So first let us talk about this. Yeah, actually, but in fact, we will start by talking about eigenvalues of linear transformations and only then go on to matrices. Because again, if I have a finite dimensional vector space, then every linear transformation can be written as a matrix in some basis. But if I have an infinite dimensional vector space, then we don't typically write down a matrix with respect to an infinite basis. So we just call it a linear transformation. And for every linear transformation, you can talk about eigenvalues. That is why I will do so. Okay. So before that, let's start with eigenvalues. Okay. So so now eigenvalues. So okay, let us start very simply. Okay, you remember, suppose I have a diagonal matrix. So I have some. Now the point is, I will keep writing eigenvalues, whatever those are. Those are always scalar numbers. I will keep writing them as lambdas. So let's start the diagonal matrix with entries lambda 1, lambda 2, lambda n. Okay. Now this matrix has a. Let's not call it that yet. How do you act on a vector? So how does this act on? How does it act? A general vector or arbitrary vector remember, this is a linear transformation. This belongs to lin fn to fn. Okay. You multiply by a vector with n coordinates, you will get a vector with n coordinates. How does this act on such a vector? And the point is, because this matrix is so nice, we can actually give a formula, an explicit formula. Answer: 2 steps. One is write down V in terms of the standard basis. Let's say summation Ci Ei in terms of the standard basis. Of f to the n. Second, now I can write down the formula trivially, right? Because I know that this matrix acts on Ei by rescaling by lambda I. And it is a linear transformation, so it goes inside. Now, d times v is very simply summation I goes from 1 to n Ci lambda I EI. That's what it is. Nothing else. Very simple. So this is true for very, very special kind of matrices, diagonal matrices. Can we say something like this for other matrices? Does this hold for other matrices? F to the n. Okay, so that's my question. Oh, sorry. Not F to the n, but F to the n cross n. The answer turns out to be yes, it does. Now, which kind of matrices? Well, a very, very simple generalization or modification of diagonal matrices. In the literature, well, in your course as well, they will be called diagonalizable matrices. But let us just do that first. Okay, so now instead, say P in F to the n cross n is invertible. I really need to switch pens now. What does it mean? And A equals P D P inverse, where D is as above. So D is a diagonal matrix, and I'm just taking what is called the conjugate of it. Pre-multiplied by some invertible matrix, post-multiplied by the inverse of that. Now I can do the same thing as well. Okay? Then A times B equals what? Well, so here is how we proceed. Again, you do the same two steps, except you use a different basis of P, of F to the n. What basis do you use? Well, notice that if P is an invertible matrix, then its rows span the entire row space, hence they are a basis of the row space, or its columns span the entire column space, they are a basis in particular, right? So you look at the columns of P. These are a basis of F to the n because the column space is F to the n. So one, P invertible implies the columns, which is, and what are the columns? They are exactly PEI. I goes from 1 to n. Those are the columns of P. Form a basis of F to the n. Let's give them a name. Vi equals PEI for all 1 less equals I less equals n. Form a basis Okay, so first of all, this is the case. Maybe I should call this step 0. This is not actually doing anything, but this is making the realization, making the connection that will help us. Okay, so now step 1 is exactly the same thing. Write B in terms of this basis. CI-VI. Okay, or you can say CI-PEI. The other way to say this is to say, well, take the P on the other side, right? P inverse V in terms of CI-EI. If you want, you can do that also. This is if and only if. Write P inverse V as the sum of summation CI-EI. Okay? So first you do that. Let me do that here as well. Okay. And now you can write down what is A times B. That is step 2. I'll just do it here. Yeah. So now A times B is how much? Well, so you can write what is A. A was P times B times P inverse times V. But what was P? This was CI times PEI. So you see the P inverse cancels with the P. Now you have the same calculation, B times summation CIEI, which is equal to lambda factor. So you get P times summation I goes from 1 to N, Ci lambda EI, lambda I EI. And then again you put back the P, and now P times EI was back again to Vi. So again the same thing. If you start with the vector summation Ci Vi, then E will give you the extra lambda factor. Just like here, if you started with Ci Ei, then the D gave you the lambda factor. What happened? What would happen if I had A square? So this is of course we are done, but similarly, out of curiosity, A square. Let's see, why do I not have homework here? What is A square? So first of all, if you have remember your midterm, A square is P.D.P inverse times P.D.P inverse. The P inverse and P cancel in the middle. You get P times D square times P inverse. So D square is the diagonal matrix with lambda 1 square, lambda 2 square, and so on, right? And so when you multiply this thing by V, what would you get? Well, the P inverse would again cancel. Then you would multiply by D square instead of D, so you get lambda I square here. And then you multiply back by P. So you get the same kind of thing. And you would just get summation Ci lambda I square V, not Pi anymore, because you put back the P. And now here is therefore homework problem. Given any polynomial in one variable, I can write down the polynomial of that matrix. Like this is x squared. I can do a cube. I can do a cube plus x squared. It's like an x cube plus x squared. So I can take any polynomial in my matrix A and apply it this way. And that is your homework. If P of x belongs to fx is a polynomial and sorry, let's say, and then D is of course as above lambda 1 lambda n diagonal matrix, and then A equals P.D.P inverse. Then I can write down, then show that. Sorry. Show that P of A. So instead of saying A times summation CIVI or A square times that, let's do P of A times summation CIVI. I mean, show that is really, it's almost trivial. You have to sort of just say by induction and linearity or something. But I figured Ci, and then this is obvious, P of lambda I, Bi. So whatever polynomial in A, you have A, then you get lambda. A square, you get lambda square. P of A, you get P of lambda. But the point is exactly that. Once you understand these VIs, then life is good. And what is special about these VIs? This crucially makes use of the fact. Basically, this is all a linearity thing, right? So linear combinations behave well if the individual constituents behave well. And what are the individual constituents in this? They're exactly the VIs. Once you know how A acts on one VI, you know how A acts on the sum of VIs or the linear combination of VIs, and you know how A square acts and so on and so forth. So at the heart of all this is the action of A on a single of one matrix A on one vector VI. At the heart of this phenomenon. So this is a very nice phenomenon, right? It says that take a general vector in F to the n. Take any vector, and I can tell you how any polynomial of my matrix A acts on that vector if my matrix A is of this form. Okay, but so that's the point. For special matrices like that, P.D.P inverse, you can explicitly directly say this without any, like I don't have to do any matrix multiplication. I don't have to compute large powers of A. I don't have to multiply A by itself many times, like A square or A cube or something. I just have to take a polynomial variable evaluated in the lambda s scalars. So it is much easier to compute the right hand side than to first compute this and then do this. Rather, you just compute this directly and it's trivial, it's easy. So you save yourself enormous amounts of time and calculation and effort, pain, if you will, if you knew such a decomposition of A. So at the heart of this linear phenomenon is the fact that A times Bi, which is of course, well, you can do the same calculation again, but I'll just take a special case. P of A is A. All the C's are 0 except Ci, which is 1. Then you just get lambda I. This is the phenomenon because of it. The moment this is true, then A square is A times Vi is lambda I times A times Vi. So lambda I times lambda I times Vi. And then you can do A cube plus A square and all these other things. So that is really the hard part. Once you know this equation for every I and a single power of A, then you know this equation for every polynomial of A and all the linear combinations of I. So this is enough. This is if and only. This is if and only if this happens. Okay. Anyway, so the point is this is what is called an eigenvector and eigenvalue. And of course, this is over a finite dimensional vector space because we are doing F to the n. But you can say this over an arbitrary vector space. This definition or this simple condition doesn't require any kind of finiteness of dimension or basis or anything, right? So great, so let's do that. So definition, yeah, so V is an eigenvalue and the lambda is the eigenvector, and that is what we will define now. Okay. So say V is a vector space over, I'm not saying finite dimensional, and P is in lin V comma V. Okay, so it's just a linear map from V to V. If there exists a V in V non-zero, and this lambda scalar, such that the linear transformation of V is equal to lambda times V. This is like A times V, A times Vi, lambda times V. We say lambda is an eigenvalue of T. So for eigenvalue, the V must be non-zero. Because for the zero vector, T times 0 is lambda times 0 for any lambda. There is nothing there. So that's really, there's no, it's completely trivial unless the vector V at least is non-zero. So if that is true, then this is an eigenvalue of T with or maybe I should say we should say V is an eigenvector of T. Eigenvector of T with eigenvalue lambda. Right, the point is lambda is uniquely determined. If I know the vector V and I know this holds, then lambda can be uniquely determined because v is non-zero. So if lambda v and mu v were both of them equal to t times v, then lambda v equals mu v, or lambda v equals lambda prime v. So lambda v minus lambda prime v is 0. So lambda minus lambda prime times v is 0. But v is non-zero. So the only scalar multiple of a non-zero vector, that is the 0 vector, is 0. So the scalar lambda minus lambda prime must be 0, therefore lambda equals lambda prime. So I'm not writing this down, but that's obvious. But once you know an eigenvector which is non-zero, the eigenvalue is uniquely determined. Okay, so examples as we saw. T equals the diagonal matrix on V, which is Fn with the standard basis. And then we know, right? Then EEI is the eigenvector with eigenvalue lambda. I am not saying that these lambdas are distinct. So maybe like the identity matrix 1, 1, 1, 1, 1. Well, then EI is the eigenvector for with eigenvalue 1 for every I. Okay, but also you can see that the eigenvalue is 1. Suppose the identity matrix. So the identity times EI equals EI. So 1 times EI. Great. But in fact, the identity times any vector equals 1 times that vector. So even if you take linear combinations of EIs, you still get eigenvectors. They still satisfy the same condition. And that is always true. So the point is, this is always true that the set of eigenvectors for a given eigenvalue, if I fix my scalar 1, which vectors are fixed by my transformation? T times v equals 1 times v. That turns out to be a subspace. It's not quite a subspace in the sense I asked for non-zero. So if I take the set of non-zero eigenvectors for a fixed eigenvalue and attach the vector 0, then that union is a subspace. Okay. So I think that may be my next result. No, I first need to define that subspace. So this is definition 1. I'll say definition 2. So given no, this is not that. This is all assumed. This is definition 1. So I'm assuming this again. I'm assuming V is a vector space, arbitrary, not finite dimensional necessarily, and T is a linear transformation. Okay. So given lambda in F, the lambda eigenspace, so eigenvalue, eigenvector, and now eigenspace. Of T is, I'll call it V lambda. So V lambda, which is equal to all the lambda eigenvectors of T union 0. Disjoint union 0. Because you can read this, right? Yeah, it's legible. It's V lambda is defined to be the set of all lambda eigenvectors of P, that's off there, union 0. Okay, now we come to the first lemma or whatever. Proposition maybe. Okay, so V lambda is a subspace. So notation is above, so V equals a vector space. And let's say lambda is in F. Then V lambda is a subspace of V. Moreover, the following are equivalent. There are 3 or 4 equivalent conditions. Basically, it's equivalent conditions for when is V lambda not equal to 0. Is that my first condition? Yeah. V lambda is not the zero vector or the zero subspace if and only if lambda is an eigenvector, eigenvalue. Eigenvalue of T if and only if and only if you look at the transform, so T is a linear transformation, therefore T minus identity is linear transformation, T minus twice identity, T minus lambda times identity. Actually, let me not just say it's a subspace, because I want to remind you of this later. So this is precisely the kernel of T minus lambda identity. And of course, every kernel is a subspace, so this is a subspace. It's more than just saying it's a subspace. I'm telling you what subspace. It is the kernel of a linear transformation from V to V. And so this is not one. These are equivalent. That is V lambda, and that is the statement of the result. Okay, let's do this. So what is the time? 34. Wow, okay, fine. I'm going really slow today, but in fine. Let's see how much I can do. Yeah, 15 minutes. Okay, fine. So that's what I wrote down. Okay, great. So the proof is very simple. I mean, if you look at this thing, right? So clearly, if you look at a lambda eigenvector, so TV, so first of all, TV equals lambda P, lambda eigenvector, if and only if T minus lambda times identity equals 0. That's just obvious. Now, the point is, if V is non-zero, these are called eigenvectors. If V is 0, then I'm including them. Therefore, that's exactly the same as the kernel of lambda minus. Right? So this is all I'm saying is TV equals lambda V. If and only this, which is the same as saying that V belongs to kernel T minus lambda identity. Now, if you know that this is true, then you're done, right? Either V is non-zero, then it's an eigenvector, a set of eigenvectors, or V is 0, and that's all. Just do the first part, and then I think 1 if and only if 2 is therefore also obvious. V lambda is not 0 if and only if there is at least one element here. If and only if if and only if this kernel is I'm doing 1 implies 3, right? So V lambda is non-zero if and only if there exists a lambda eigenvector, lambda eigenvector actually I don't need to say anything more, right? V lambda is not 0 if and only the kernel is not 0. The kernel is not 0 is the same as saying this is not 1 to 1. This is obvious. This is 1 implies 3 is obvious because of the fact that V lambda is the kernel. What about 1 implies 2 or if and only if 2? V lambda is not 0 if and only the kernel is not 0. If and only if this space, this set is non-empty. But that means lambda is an eigenvalue. So this is also obvious. Okay. The whole thing is obvious. Fine, great. So now what am I saying? So now this is for an arbitrary vector space. I did not say finite dimensional or infinite dimensional. Now let me restrict to the case when V is finite dimensional, and then we get to a matrix and so on and so forth. So this is all well and good. In fact, this is all very nice. But why am I doing this restriction? Well, I want to calculate these things. Okay, this theoretical concept of an eigenvalue is very nice. It's nice, it rescales. But how do you know if one exists? And if one exists, how do you know what it is? And if you know what it is, how do you calculate the eigenvectors? So how does one actually do that? So how to find that? So okay, from now on, I will call them E values, eigenvalues, and E vectors. So the point is you can do this if the vector space is finite dimensional. I mean, by can be done means somebody, like an all-powerful computer can do this. If dim v is less than infinity. So how does it work? That is the part that I want to sort of say as much as I can, and then we will stop. So that's the corollary here. Corollary to that obvious proposition. Say V is finite dimensional and T is 0. So V is a finite dimensional vector space over F. T is in lim VV and lambda belongs to F. Do I still want to say the following are equivalent? Yes. The following are equivalent. Okay, so what are the conditions now? I will basically have these conditions and a couple of others. Let me just mention one of these conditions, and so automatically all the others are also equivalent to it. Equivalent to it. Yeah. Yes, I'll just mention the condition maybe that lambda is an eigenvalue, I guess. Yeah, why not? Yeah. So actually it's like 2, 3, and 4, but fine. Maybe I'll say that. So lambda is an eigenvalue of T. 3. Something's very wrong. 3 is the T minus lambda identity. Is not 1 to 1, or is not 1 to 2, or is not an isomorphism. I'm just squishing it there. And the fourth condition, the extra condition that is equivalent. So 2 is literally 2, 3 is literally 3. And the 4 is that you take the determinant. So earlier I could not define determinants, but now I will. Because now it's finite dimensional, and this is where the proposition, fact, corollary, lemma, last thing I proved. The determinant of a linear transformation makes sense if, regardless of which order basis you choose. So I can say determinant T minus lambda identity equals 0. And again, I should remind you that this is with respect to any order basis B. That was what we just proved before starting determinants. Okay, so why is this true? Well, 2 if and only 3 was already proved. The only question is why are these equivalent? But that we've already seen, right? For a finite, so I gave you this analogy. Remember, for a finite set and a map from a set to itself, the set theoretic map is 1 to 1 if and only if it's onto if and only if it's a bijection. And the same kind of thing by the rank nullity theorem was true for linear maps. From a finite dimensional vector space to itself, such a map is 1 to 1 if and only if onto if and only if bijection. So this was done in class. These 3 are equivalent. The 2 and 3 are equivalent is already here. 3 and 4 or whatever. Well, but now that's the inverse part, right? Isomorphism or invertible. I can also write down invertible here, and maybe that's what I should just do. This is a linear transformation. Fix any ordered basis. And this is a matrix. A matrix is invertible, is not invertible if and only if its determinant is 0. That's all. It's very simple. So proof is obvious, or exercise, or check. But there's nothing to say. I mean, these 2 if and only if are there. These 3 equivalences are done in class. And non-invertible if and only determinant is 0 is also done in class. So that's that. Okay, so that was the corollary. Now, how does one calculate, right? So let's do an example of how to calculate this polynomial. and maybe that's where we can stop. So back to the how to calculate part. So now let's do an example. So using this corollary, let me use blue pen now. Last 10 minutes, I can focus. Using this corollary, here is how we calculate. All the tuples lambda eigenvalue and v lambda from T. From T or from A. I mean, you have a finite dimensional vector space. As I said, the first thing is to fix an ordered basis, make a matrix out of it, and then do this calculation. So let me just do it for A. So example, T, let's just say equals A equals 1, 1, 1, 1 on F2. So this is equal to V. So N equals 2, V equals F2, and T with respect to standard basis is this matrix. How do you calculate this thing? Well, what you do is very simple. You want to say determinant of T minus lambda identity is 0, where lambda is a scalar. Let's calculate that. Okay. Except now for whatever algebraic reason, I will use lambda identity minus T. So every eigen, so now lambda is a scalar, then lambda belongs to F is an eigenvalue of A if and only if the determinant of lambda identity minus A is 0. Why? Because again, I can just, the expansion of this is like, you can check this is equal to determinant of A minus lambda identity. In general, it is plus or minus 1 times lambda. That's also not hard to check. Okay. That's obvious actually, but fine. Okay, so what is this? But this is equal to is what is lambda minus 1 minus 1 minus 1 lambda minus 1. Determinant, sorry. And so you get AD minus BC, which is lambda minus 1 square minus minus 1 square. And you can check this is lambda square plus 2 minus 2 lambda plus 1 minus 1, so it's lambda square minus 2 lambda. Lambda times lambda minus 2. Okay, great. So now what do we do? When is this equal to 0? This is equal to 0 if and only if lambda is 0 or lambda is 2. You are in a field. So either lambda is 0 or lambda is 2. 2 means 1 plus 1. So this happens. So yeah. So lambda is an eigenvalue of A. One plus 1, which might be 0 in characteristic 2, but otherwise it is not 0. And now how do you calculate the lambda eigenspace? Remember, that's what all we want to do is compute these guys. Okay. So first of all, that means that for all other lambda, the V lambda is equal to 0. That was the exact proposition that I just deleted here, right? If lambda is not an eigenvalue, then V lambda is 0. So that is clear. It's only these two for these two that you check. And now how do you check what is V lambda? Well, you know exactly what is V lambda. I deleted that also. It is the kernel of lambda A minus lambda identity, or lambda identity minus A. And for lambda equals 0, 2, I'll just write 2. Okay, let's assume the characteristic is not 0, whatever. V lambda, compute V lambda, which is the kernel of, again, you can say A minus lambda identity, you can say lambda identity minus A, it doesn't matter. And you can compute it, and I'll just write down the answer, but that is like, how do you compute a kernel of a space? You solve Ax equals 0. So solve, maybe I'll just say that, i.e. solve it. You know how to solve linear systems, so I'll just tell you the answer. So in fact, we get answer. Lambda equals 0, lambda equals 2. Let's say 0 not equals 2 in the field. Then what you get is the and what you get is V lambda is the F span of 1 and minus 1. Or you could say minus 1 and 1 if you multiply by a scalar, that's also the same thing. V lambda is the F span of 1 and 1. That's the answer. So that's how you compute eigenvalues and eigenvectors. There is no subtlety. The main thing is the eigenvalues. Basically, you have to plug in this lambda as a scalar into lambda identity minus A and take the determinant. And as you can see, this gives you a polynomial. Lambda, it's a quadratic polynomial because here it's a 2 by 2 matrix. In general, it's an nth degree polynomial with top coefficient 1. And that's exactly where we will start next time. This is called the characteristic polynomial of the matrix or of the linear transformation. Because again, as we will talk next time, the characteristic polynomial of a linear transformation does not depend on which ordered basis you choose. So you can just say take any ordered basis, take the characteristic polynomial, find the roots of that polynomial in the field. Maybe sometimes there are no roots. You might get lambda squared plus 1 over the real numbers. And lambda squared plus 1 for any real number is strictly positive. So maybe there are no roots. But whatever roots there are, those are precisely the eigenvalues in the field. And then the corresponding kernel is the eigenspace. Okay, so that is it for today. We will continue next time, next week. So